Section 10.2 is about logarithms and logarithmic functions. Since you can have an exponential function y equals 2 to the x, you can define its inverse then as x equals 2 to the y by just switching the x and y. Well, it's this inverse that we're going to look at today, because in general this inverse is called the logarithm of x. If you have an x equals 2 to the y function like you do right here, we call that inverse the logarithm. And we write it this way: y equals log base b of x. Now what that means is if you have a base, right here, base b, and you take it to the y power, it will equal this value, or in this case equal x. That's what the pieces represent when you have a logarithm, or in short, when you have a log. Here is the definition of a logarithm with base b, which is just what I was telling you. The base b to the y power equals x. That's what a log is. And then we're going to use this idea to just examine different kinds of functions with exponents. So here we have some examples that we have to write in exponential form. These are right now in log form. So remember I said that the base, the little b, so 8, to the 0 power in this case, and that's going to equal the x value, because remember we said the base is from here, the power is after the equal sign, and then what's after the log, that's what the exponential form actually equals. Now, is this true? Does 8 to the 0 power equals 1? And the answer is yes. So you can see the relationship between the exponential form and the logarithmic form. Likewise over here, base 2 to the negative 4th power is 1 over 16. And that's true because you have to make this 1 over 2 to the 4th, which is 1 over 16. Now if you go down here and you have things that are in exponential form with exponents, can you write them in logarithmic form? And so we would say log base 10, so a little 10 down here because that's the base, of 1,000 equals 3, because 3 is the exponent. And then over here, log base 9 of 3 equals the exponent of 1/2. And so that's how you convert from log to exponents, and then from exponents to logs. So here we have a log that we have to evaluate. Log base 2 of 64 is another way of saying 2 to what power equals 64. That's what log base 2 of 64 is really saying. So from the last section, if we could write these both as 2 to some power, then I could set them equal. Well, 64 is 2 to the 6th power, and now that the bases are the same, we can say that y equals 6. And so evaluating this, we can say log base 2 of 64 equals 6. Now here's a discussion on the fact that exponential function, which is b to the x, and the logarithmic function, which is log base b of x, these are inverses of each other. And if they're inverses of each other, you see a demonstration on how the composition has to equal the identity function. In other words, the composition has to equal x. So when you take a base and you take that to the log base b power, those two things end up wiping each other out, leaving you whatever the value after the log is. Likewise, if you have a log base b and you take that of b to the x power, you end up wiping the log and the base out, leaving the exponent x, which is the identity function. In other words, the log function and the exponential function are inverses, just like squares and square roots, and they undo each other. So if you go down here at these examples and you say log base 6 of 6 to some power, those wipe each other out, leaving just an 8. And then likewise over here, if you take a base to the log base 3 power, those wipe each other out, leaving just a 4x minus 1. So the fact that they're inverses of each other, it's a powerful tool that we can use to simplify equations. Now we will look at a logarithmic equation, which is just an equation that contains at least one log in it. And we're going to try to solve this for the unknown. Well, the best way to solve this is to write it in exponential form. Since log base 4 of n equals 5/2, we can then say that 4 to the 5/2 equals n. And now we can simplify this side. We know that a fractional exponent, like a 1/2, if I were to rewrite this as 4 to the 5th to the 1/2, we know that really means square root. And then we could put the 5th power on the outside. And we know the square root of 4 is 2, so this is really just 2 to the 5th power equals n. And then we can say that n is 32. And that's just using the fact that we can turn a log into an exponent and then do some simplification that we've done in the past. Here we're going to look at logarithmic inequalities, just inequalities that have logarithms in them. And those say that if you have a log with an inequality symbol and you turn it into exponential, the inequality symbol stays the same. The only thing that might be a little different is if you have a less than sign, you need to make sure that when you turn it into an exponential that you're never going to go less than 0. Because if you turn this into an exponential function, the base will always be a whole number, and therefore you're never going to get a number that is smaller than 0. So if I go down here, I see it's less than, and if I look at my less than part of the key concept says I'm going to take my x, and I'm going to make it smaller than the base, which, my base is 5, to the exponent of 2. But I'm also going to say that my x can't go below 0. So here's how I'm going to rewrite my log as an exponential function. So I can say that 0 is less than x, which is less than 5 squared, which is 25. So that's how I can evaluate my log. Here's another property of logarithms, and it says that if you have a log with a base, and that equals another log with the same base, if you can get those to match up, then you can just set the values after the logs equal to each other. So in this example, I have two log base 5s, and since they're both log base 5s, then I can just say that p squared minus 2 has to equal p. I can drop the logs and then solve this like normal. I'm going to bring the p over here and make it a polynomial. Two factors of -2 that add to be -1 are -2 and 1. So I'm factoring this using the diamond, which means I find that p is 2 and p is -1. Now you have to be careful with logs. You got to plug these back in and make sure that they actually do work. So I'm going to go over here and I'm going to try the 2. So we're going to say log base 5 of 2 squared minus 2. Does that equal log base 5 of 2? Well, 2 squared is 4, and 4 minus 2 is 2. So yes, we can see that when I plug a 2 in, I get a log that actually works. So that one's correct. Now I'm going to try -1 and see what that does. So log base 5 of -1 squared minus 2, does that equal log base 5 of -1? Well, -1 squared is 1, and 1 minus 2 is -1. Now, it would appear that that works, but you cannot have negative values in your logs. And I'll point you back to the definition of logarithms at the very beginning of the section. It says let b and x be positive numbers. You can only have positive bases, and you can have only positive numbers after the word log. Those are the only values that can be calculated using logarithms. So when we go back to our example, we see that -1 can't be negative, so p equals -1 is an extraneous solution. So our only solution in this particular problem is p equals 2. And our last slide here is a property of logarithms with inequality symbols, and it just says that if the bases are the same, then the inequality symbols are going to stay the same. Both of these examples have log base 10, so I can just set 3x minus 4 less than x plus 6, keep the symbol intact, and then solve it as normal. 2x minus 4 is less than 6, we'll add 4. So 2x is less than 10, divide by 2, and you're going to get x is less than 5. Now, because logs have certain restrictions, we also have to look out for 3x minus 4 being greater than or equal to 0. It has to be positive. So if we solve this, we get x is greater than or equal to 4/3, and we also have to check for x plus 6 greater than or equal to 0. So we get x has to be greater than or equal to -6. So we've got to combine all three of these. We want numbers that are bigger than 4/3, that are bigger than -6, and that are less than 5. Well, the only numbers that are bigger than -6 are also the ones that are bigger than 4/3. So we need them to be both of these. So really we're just looking for numbers that are bigger than 4/3, but smaller than 5. So this would be my final solution, my final answer, because this includes all the values that will make my logs positive values.